creating both the test2 and nudistdir folders, and you were able to change into nudistdir to prove the point. Note that os.makeDirs raises an error if the target folder already exists. You can use a couple of additional parameters to further tune the behavior, but the default values are usually what you need. Another module, Tuple, provides a set of higher-level file manipulation commands. These include the ability to copy individual file, copy whole directory trees, delete directory trees, and move file or whole directory trees. One anomaly is the ability to delete a single file or group of file. That is actually found in the OS module in the form of the os.remove function for file, and os.remodir for empty directories, although Tuple.remotree is more powerful and usually what you want. Another useful module is glob. This module provides file name wildcard handling. You are probably familiar with the and asterisk wildcards used to specify groups of files in the OS commands. For example, star.exe specify all files ending in .exe. Glob.glob does the same thing in your code by returning a list of the matching file names for a given pattern. Try it out using wildcards, copying, deleting, and moving files. In this try it out, you use the functions from OS, glob, and Tuple to manipulate whole files. Follow these steps. 1. Change into the root directory created earlier. 2. Create a new file called test.py, it doesn't really matter what is in it, you are only interested in the name. 3. Start the Python interpreter and type in the following code. Import os glob Tuple as shos.listdir. Hashtag everything in the folder, file a.txt, file b.txt, ls.txt, subdir, test.py, test2 glob.glob, hashtag everything in the folder, file a.txt, file b.txt, ls.txt, subdir, test.py, test2 glob.glob, hashtag files with an extension, file a.txt, file b.txt, ls.txt, test.py, glob.glob, .txt, hashtag text files only, file a.txt, file b.txt, ls.txt, glob.glob, file.txt, hashtag text files starting with file a.txt, file b.txt, glob.glob, star. Hashtag any file with a 2-letter extension test.py. 4. Look closely at the different result sets to see the effect of the different function/argument combinations. 5. Type the following code. shcopy, file a.txt, file x.txt, shcopy, file b.txt, subdir/file y.txt, os.listdir. File a.txt, file b.txt, file x.txt, ls.txt, subdir, test.py, test2 os.listdir, subdir, file y.txt. Accessing the operating system 65. shcopy tree, subdir, test3, os.listdir. File a.txt, file b.txt, file x.txt, ls.txt, subdir, test.py, test2, test3 os.listdir, test3, file y.txt, shremotree, test2, os.listdir. File a.txt, file b.txt, file x.txt, ls.txt, subdir, test.py, test3. 6. Review the output from the commands you just typed and consider their impact before typing the following code. os.mkdir, test4, shmove, subdir/file y.txt, test4, os.listdir, test4, file y.txt, os.listdir, subdir, os.remove, test4/file y.txt, os.listdir, test4, os.remove, test4, traceback, most recent call last file, line 1, in OSERR, no 1 operation not permitted, test4 shremotree, test4, shremotree, test3, os.remove, file x.txt, os.listdir. File a.txt, file b.txt, ls.txt, subdir, test.py. How it works. In the first set of commands, you compared the effect of os.listdir with various patterns in the glob.glob function. The first pattern, asterisk, replicated what os.listdir did by listing the full contents of the folder. The second pattern listed all files with an extension. Strictly speaking, glob does not know anything about files or folders, it works strictly with names, so it actually listed all names that had a period included regardless of what kind of object it was. Next you used the star.text pattern to find all the text files followed by file. Text to find any text file whose name starts with file followed by a single character. Finally, you used a combination of wildcards to find any file whose name ends in 2 characters, star. The second set of commands looked at the Tuple file manipulation commands. You started by using Tuple.copy To copy single files, file a.txt to a new file in the same folder called filex.txt and file b.txt to the subdirectory subdir with a new name file y.txt. You then used os.listdir twice to see the results in each folder. You next looked at directory-level operations with the shuttle.copytree function that copied the subdir directory and its contents to a new folder, test3, creating it in the process. Again, you used os.listdir twice to conf-rm the results. You used shuttle.remtree to delete the test2 folder and its contents. Once again os.listdir proves the point. 66 Chapter 2 Scripting with Python. You started the next sequence by creating another new folder, test4, using os.mkdir. Into this new folder, you moved the file y.txt using shmove. Again, using os.listdir on both folders proves that the operation succeeded and the file no longer exists in subdir but does exist in test4. Finally, you looked at removing file a with os.remove. The first example removed the file from test4 and verified that it had been deleted. The next line attempted to remove test4 itself, but produced an error because os.remove works only on file a. If you need to remove a directory, you need to use shuttle.remtree again, or you could have used the os.remdir function to the same end. You finished by using os.listdir once more to conf-rm that the folder had gone. If you look at the shuttle documentation, you'll see several variations on the copy functions with subtly different behaviors. In most cases the standard shuttle.copy function does what you want. Other features of shuttle include the ability to create archived or compressed files in either zip or tar formats. Also, you can extend the functionality of several of the functions using optional arguments. One of the most interesting is the shuttle.copytree function, which has an ignore parameter. You can set this to a function that takes two arguments, a root folder and a list of files. The function must accept two parameters even if they are not actually used by it. The function then returns another list of file names that shuttle.copytree ignores. This function is then called by shuttle.copytree for each folder of the tree being copied, with the arguments being the current folder within the tree and the list of files produced by os.listdir, acting on that folder. This is useful for ignoring temporary or archive files, or files that can be recreated later. Here is a short example that copies a project directory tree but ignores any compiled Python files, i.e., those with an extension of .pyc. Def ignore _pyc, root, names, return name for name and names if name.ends with pyc, hashtag now test that it works ignore _pyc, fred1.py, 2.py, 2.pyc, 4.py, 5.pyc, 2.pyc, 5.pyc, sh copytree, projdir, projback, ignore =ignore_pyc. In this case you used a list comprehension to build the ignore list, but you could equally just return a hard-coded file name, for example RCS to avoid copying version control file A across, or you could have a much more complex piece of logic involving database lookups or other complex processing. The scenario of testing for a standard pattern, star.pyc, in your case, is so common that shuttle has a helper function called shuttle.ignore_patterns, which takes a list of glob-style patterns and returns a function that can be used in shuttle.copytree. Here is the previous example again, but this time using shuttle.ignore_patterns. sh copytree, projdir, projback, ignore =sh ignore_patterns, star.pyc. Remember that the ignore function is called for every folder being copied, so if it is very complex, the copy tree operation could become quite resource-intensive and slow. Finally, consider a submodule of OS called os.path. The os.path module contains several helpful tests and utility functions that can help you when using the higher-level functions already discussed. The most useful functions are for creating paths, deconstructing paths, expanding user details, testing for path existence, and obtaining some information about file properties. Accessing the operating system 67. You start your exploration of os.path by looking at some helpful test functions. You saw earlier how you can use os.stat to extract information about a file. os.path provides some helper functions that get the more common features more easily. You can, for instance, determine the size of a file using os.path.getSize, the modify cation time using os.path.getTime, and the creation time with os.path.getTime. You can also tell whether a name, returned by os.listdir, for example, is a file or a directory using os.path.isFile, or os.path.isdir. You can even test for mount points and links if that is important to you. All of these functions take a name as an argument and return true or false. That's a bit easier than calling os.stat, and then using a combination of indexing and bit masking to extract the details. The next thing that os.path helps with is processing paths. You can find the full path to your file using os.path.obspath, and, if it's a link, the path to the real file with os.path.realpath. Having obtained that path, you can break it into its constituent parts. Python considers a full file path to look like this. Using os.path.splitDrive, you can read the drive letter, if you are on Windows, otherwise it is empty. os.path.dirname, finds the folder, and os.path.basename, gets the file name, including the extension. You can even get the folder path and file name in one go with os.path.split. Usually that's sufficient, but, if necessary, you can further split the file name into its extension and core name with os.path.splittext, in which case the extension includes the period, for example, mfile.exe returns mfile and.exe. Often, after having inspected and worked with the various path components, you want to reassemble the path or even create one from scratch. os.path provides another convenience function for this called os.path.join, which takes the various elements and combines them into a single string using the current os path separator, as defined in the constant os.september. This is very important because path format is one area that varies considerably across operating systems. Since Mac OS X appeared, based on a Unix kernel, things have been a little easier because Windows usually accepts the Unix style/separator in addition to its native / style. But it is still safer to use os.path.join to create file paths if you plan on running your script on multiple computer types. You can see this operation in action on your test files and folders. Try it out working with paths. In this try it out, you use the os.path functions to determine the status of various files. To see them in action, complete the following steps. 1. Change into the root directory you created earlier. Stay in the OS for the moment. 2. Using the OS, copy file a.txt into the subdirectory subdir as file c.txt. 3. Now create a symbolic link to file b.txt in subdir and call it file.txt. If you are on Windows, you probably don't create symbolic links, so you need to miss out on the steps associated with file.txt. The Unix command for this is $lns file b.txt subdir /file.txt. 68 Chapter 2 Scripting with Python. 4. Fire up Python and type the following code. Import os from os import path os.listdir. File a.txt, file b.txt, ls.txt, subdir, test.py, path.getSize, file a.txt, 257 path.getTime, file a.txt, 138910937.10449222 path.getSize, subdir /file c.txt, 257 path.getTime, subdir /file c.txt, 13892747067366207 path.obspath, file b.txt, /home/agawld/book/root/file b.txt, path.obspath, subdir /file.txt, #not Windows, /home/agawld/book/root/subdir/file.txt, path.ilink, file b.txt, #not Windows false, path.ilink, subdir /file.txt, #not Windows true path.realpath, subdir /file.txt, #not Windows, /home/agawld/book/root/subdir /file b.txt, folder, file name equals path.split, path.obspath, subdir /file b.txt, print, folder, file name, /home/agawld/book/root/subdir file b.txt path.join, folder file name, /home/agawld/book/root/subdir /file b.txt, path.splittext, file name, file b.txt. How it works. You started off by importing the modules you need and checking the contents of the current folder, just to check that you are where you expect to be. You then compared the size and creation time of file a.txt and subdir /file c.txt, which was a copy of file a.txt if you recall. You see that the sizes are identical but the creation times different, as you'd expect. You next looked at file b.txt and its linked relation file.txt. This time you looked first at the absolute path to each file. Both show up as you'd expect in their respective places. You then tested both files to see if they were links. Of course, file b.txt is not, but file.txt yields a positive result. You next asked for the real path to file.txt, and it revealed that the original was, in fact, file b.txt. Finally, you looked at some path manipulation. You used os.path.split to break the file b.txt path into the folder and file parts. You joined them back together with os.path.join, and then you split up the file name to get the core name and the extension. Notice the period is preserved at the front of the extension. Accessing the operating system 69. Plumbing the directory tree depths. One common automation operation is to start at a given location and apply a particular action to every file E, or type of file E, in the file E system below that location. This is often called walking the directory tree, and the OS module contains a powerful and fluid executable function called os.walk that helps you do just that. It is not the most straightforward function to use, so you spend this section looking at its key features. You consider an example of os.walk being used to find a specify C file E located somewhere within a given directory tree or subtree. You then create a new module with a find file function that you can use in your programs. That foundation can go on to form the basis for a whole group of functions that you can use to process directory trees. First, you need to create a test environment consisting of a hierarchy of folders under a root directory. You can generate this structure by extracting the file e treeroot.zip from the chapter2.zip master file e on the download site and then extracting the file s within treeroot.zip, or you can use the OS tools to generate it manually. Each folder contains some file s, and one of the folders contains the file e you want to find, namely target.txt. You can see this structure here. treeroot.fa.txt, fb.txt, d1fc.txt, d1-1ff.txt, d2fd.txt, d3fa.txt, d3-1target.txt. The os.walk function takes a starting point as an argument and returns a generator yielding tuples with 3 members, sometimes called a 3-tuple or triplet, the root, a list of directories in the current root, and a list of the current file A in that root. If you look at the hierarchy you have created, you would expect the top-level tuple to look like this. treeroot, d1, d2, d3, fa.txt, fb.txt. You can check that easily by writing a for loop at the interactive prompt. Import os for t in os.walk, treeroot, print, t. treeroot, d1, d2, d3, fa.txt, fb.txt, treeroot/d1, d1-1, fc.txt, treeroot/d1/d1-1, ff.txt, treeroot/d2, fd.txt, treeroot/d3, d3-1, fa.txt, treeroot/d3/d3-1, target.txt. 70 Chapter 2 Scripting with Python. This clearly shows the path taken by os.walk, starting with the first directory at the top level and drilling down before moving on to the next directory and so on. It also shows how you can take a file E from the file S list and construct its full path by combining the name with the root value of the containing tuple. By writing your function to use regular expressions, and to return a list, you can create a function that is much more powerful, but also slower, than the simple glob.glob that you saw earlier. Try it out building a file finder, file_tree.py. In this try it out, you build and test a module containing a file finding function using the os.walk function as a foundation. To build the module, complete the following steps. 1. If you haven't done so already, create a test directory structure like the one just described, or load it from the zip file e. 2. Go to your project directory where you keep your Python modules. 3. Open your favorite text editor and type in the following code, or load it from the zip file e. #file_tree.py module containing functions to assist hashtag in working with directory hierarchies. Hashtag based on the os.walk function. Import os, re-import os.path as path. Def find_files, pattern, base equals dot. Finds files under base based on pattern. Walks the file system starting at base and returns a list of file names matching pattern. regex equals recompile, pattern, matches equals for root, dirs, files in os.walk, base for fn files, if regex.match, f matches.append, path.join, root f, return matches. 4. Save the file e as file_tree.py. 5. Go to your root folder, that is, the one above treeroot. 6. Start the Python interpreter and type the following to test the new function. Import file_tree help, file_tree, help on module file_tree. Name file_tree. Accessing the operating system 71. Description #file_tree.py module containing functions to assist in hashtag working with directory hierarchies. Hashtag based on the os.walk function. Functions find_files, pattern, base equals dot. Finds files under base based on pattern. Walks the file system starting at base and returns a list of file names matching pattern. file/sigdrive/d/python code/chapter2/file_tree.py. 7. Type Q to exit the help screen. File_tree.find_files, target.txt, treeroot, treeroot/d3/d3-1/target.txt, file_tree.find_files, f, treeroot/fa.txt, treeroot/fb.txt, treeroot/d1/fc.txt, treeroot/d1/d1-1/ff.txt, treeroot/d2/fd.txt, treeroot/d3/fa.txt, file_tree.find_files, \txt, treeroot, treeroot/fa.txt, treeroot/fb.txt, treeroot/d1/fc.txt, treeroot/d1/d1-1/ff.txt, treeroot/d2/fd.txt, treeroot/d3/fa.txt, treeroot/d3/d3-1/target. How it works. The function takes a regular expression as the parameter pattern and compiles it for efficiency. It then calls os.walk, in the usual way using the base parameter value, and at each level of the tree tests each file found against the input pattern. If it finds a match, it generates the full path and adds it to the result list. Once all the files in the directory tree have been tested, it returns the list of found files. You tested the code by importing the module and running the help function on it. You saw the comments and docstring describing how to use the function. After exiting help, you tested find_files by searching for the literal name of your file target.txt and found the result treeroot/d3/d3-1/target.txt. You then experimented with some regular expressions. Note the differences between the glob, wildcard syntax and the regular expression form. F** indicates any file starting with F followed by 0 or more characters. *\text indicates any sequence of characters followed by a literal period and the 3 characters text. Finally, you tried using a pattern that matched directory names and got back an empty list, which is to be expected because the function only checks the file names, it doesn't look at the names in the dir's tuple element. You've seen how Python helps you work with the OS. In the next section, you see how Python enables you to work with dates and times. 72 Chapter 2 Scripting with Python. The easiest way to come to grips with these functions is to play with them at the Python prompt. You can try it out now. Working with dates and times. One of the most common features of scripting tasks is the use of dates and times. This could be to identify file A older than a certain date or between a certain range, or it might be to set a process to run at a certain time or interval. You might need to compare dates and times in data to select an appropriate subset of a file's content. Reading dates and times and comparing their values is necessary in many scenarios. Unfortunately, dates and times are not clearly defined values like integers or floats. They tend to be stored in strings with a multitude of formats. For example, 20160207, February 7, 2016, and July 2, 2016 are all possible representations for the 7th day in February, 2016. The situation is further complicated by the possibility of rendering months and days using name abbreviations such as Jan, Feb, or Monday, Tuesday, and so on. Add the fact that years may be abbreviated to 2 digits and the separators can be any of a number of characters, and you start to see the complexity. How can you reliably read a date value from a given string? Time values are almost as complex, especially if you have to consider time zones and daylight saving rules. Fortunately, Python offers several modules to help you do just that. The most basic is the time module, augmented by the datetime module and, for some tasks, the calendar module. Using the time module. The time module stores times, including dates, in 2 different formats. The phi_rst is the number of seconds since the epoch, which is simply a phi_xed date in history. For Unix-based systems that's January 1, 1970. Did you notice that's yet another date representation? The other representation is as a tuple of phi_elds representing the various parts of a date/time, year, month, day, hour, minute, second, and so on. The details are all found in the time module documentation, but you need to remember which underlying format you are using. The time modules contain various conversion functions to switch between them. 2 very important functions for reading and writing times as strings take into account most of the issues just discussed. These functions are called striptime, the P stands for parse, and strftime, the F stands for format. The secret to using these functions lies in a format string. This string tells the function how to map string values to / from time values. The format string uses % markers to indicate a phi_eld and a set of character codes to indicate what the phi_eld should contain. For example, %y indicates a 4-digit year whereas %y indicates a 2-digit year. %m indicates a 2-digit month, and %b indicates the full month name, taking into account the local language settings. A table in the time module documentation for strftime provides the definitive list. Note one quirk of the time string functions of which you should be aware is that the strftime function takes the format string as its first argument and the tuple to convert as its second. The strptime function takes the input string as its first argument and the format string as its second. Working with dates and times 73. Try it out formatting dates and time strings. In this try it out, you see how to use the strptime and strftime functions. To do so, complete the following steps, but also feel free to experiment with other variations to consolidate your understanding. 1. Start the Python interpreter and type the following code. Import time as t now equals t.time, #note, current time will be a different value each time now 13945366992.95813 GMT equals t.time, now, GMT time.struct_time, tm_year equals 2014, tm_Monday equals 3, tm_day equals 11, tm_hour equals 11, tm_min equals 18, tm_sec equals 12, tm_day equals 1, tm_day equals 70, tm_ist equals 0, 2. Look at the two formats for now, seconds since the epoch and GMT, a time tuple representing GMT, or UTC, time. Next, you use the tuple version to play with strftime. 3. Type the following code. T.strftime, the date is, %y%m%d, GMT, the date is, March 11, 2014, T.strftime, the date is, %b%d, %y, GMT, the date is, Mar 11, 2014, .strftime, the time is, %h%m%s, GMT, the time is, 11 hours 18 minutes and 12 seconds, T.strftime, it is now %i%m%p, GMT, it is now 11:18 a.m., T.strftime, the local time format is, %x, GMT, the local time format is, 11 hours 18 minutes and 12 seconds, T.strftime, the local date format is, %x, GMT, the local date format is, March 11, 4. Look at the reverse operation using strptime, by typing the following code. dt equals t.strptime, Saturday, March 8, 2014, %a, %b%d, %y, dt time.struct_time, tm_year equals 2014, tm_Monday equals 3, tm_day equals 8, tm_hour equals 0, tm_min equals 0, tm_sec equals 0, tm_day equals 5, tm_day equals 67, tm_ist equals 1, dt equals t.strptame, Saturday, March 8, 2014, %a, %b%d, %y, traceback, most recent call last file, line 1, in file /usr/lib/python 3.2/_strptame.py, line 482, in _strptame_time tt equals _strptame, data_string, format, 0 file /usr/lib/python 3.2/_strptame.py, line 337, in _strptame, data_string, format, value error, time data, Saturday, March 8, 2014, does not match format, %a, %b%d, %y, dt equals t.strptame, Saturday, March 8, 2014, %a, %b%dth, %y, 5. Notice that the format string must match the input string exactly. The use of a th postfix x on the day completely confused the strptame function. 74 Chapter 2 Scripting with Python. 6. Try a few more examples. T.strptame, 201400101, %y%m%d, time.struct_time, tm_year equals 2014, tm_Monday equals 1, tm_day equals 1, tm_hour equals 0, tm_min equals 0, tm_sec equals 0, tm_day equals 2, tm_day equals 1, tm_ist equals 1, t.strptame, 201400101 t15:05:45, %y%m%dt%h%m%s, time.struct_time, tm_year equals 2014, tm_Monday equals 1, tm_day equals 1, tm_hour equals 15, tm_min equals 5, tm_sec equals 45, tm_day equals 2, tm_day equals 1, tm_ist equals 1, t.isktime, GMT, Tuesday, March 11th, 11 hours 18 minutes and 12 seconds 2014, t.time, dt, 139423680.0. How it works. You started by importing the time module and, to save typing, you assigned it an alias, You then used the time.time function to get the current time. This should reflect the current time on your computer, so the values will be different from those shown. In fact, the values should be different every time you call the function. The now variable contains the time expressed as seconds from the epoch. Note that it is a decimal value. The part after the decimal point is dependent on your operating system and computer clock for its accuracy, so may not be as precise as it appears. The seconds representation is useful for doing simple time calculations, such as timing the duration between two events in your code. Consider using the date-time module discussed in the next section for more complex calculations. You next converted the time in seconds to a time tuple, which is the format you need for the string formatting functions to work. The tuple representation enabled you to confirm that the now value really is storing the current date and time. You then used strftime to print out the stored time in various formats. Note that the format string can have any string text within it, not just the special formatting characters. For the next set of instructions, you used the strftime function to convert a string into a date tuple. The first example used a well-formatted string to store the value in a variable called dt. The next example used a less well-formatted string in that it had a postfix after the day value. The strftime parser is not able to handle this format, so you need to add the postfix to your string value. This becomes awkward when reading strings in this format, and you may need to use a try/except structure with a combination of postfix st, nd, rd, th, to get it